All right, now we're going to do question 4.8. So 4.8, a piston cylinder device initially contains 0.2 kilograms of air at 2.5 megapascals and 350 degrees Celsius. The gas is first expanded isothermally to a pressure of 600 and then compressed polytropically with N equals 1.2 back to the initial pressure, and finally compressed at constant pressure to the initial state. Calculate the boundary work in kilojoules for each thermodynamic process and find the net work for the cycle. Okay, so there's quite a bit to unpack here before we get started. So piston cylinder device, we're given the mass, we're given the initial pressure and temperature. Of course, it's air, so we can use the ideal gas law to help us out here. That'll give us some volume, because remember, work is always about the change in volume. So, of course, with the information given in state one, we can find the initial volume. And then, of course, using the polytropic, knowing that PV to the N equals PV to the N, we can then find the next volume, because we know the volume at the end of the polytropic process is the initial pressure, right? So we sort of have like three states here. We're going from 1 to 2 to 3, but really we're told, because it's a cycle, we're always going back to the initial state. So really 3 is equal, sorry, why did I strike through? It's just the opposite. State 3 is really equal to state 1. So we're going from this state back to this state, but before that, we're going to go to state 2, where state 2 is whatever is 600 kilopascals and whatever the volume happens to be after a polytropic compression to that pressure. And then, of course, we're going back to state 1, not in the same way. The path is different, right? One path was isothermal, going from 1 to 2, and then going back from 2 to 3, or 2 to 1, because 3 is 1. We're not doing isothermal, we're doing constant pressure. And this is a cycle. And why is it a cycle? Because you end where you start. So you can just as easily do the same thing over again, right where you left off. You don't need to bring yourself back to the initial state. You already have done that as part of the cycle. Okay, but what are they asking us? They're asking us to find the boundary work for each process and then the net work for the cycle. Okay, so the net work is basically the sum of all the works done in each process. So we have work going from 1 to 2. We have work going back from 2 to 3. So the net work is going to be the sum of those two works. Okay, and of course this is a good intro to the sort of cycles you'll be doing later on. You're going to see that each cycle consists of a series of sort of sub processes, and each process has either a heat or a work interaction, and you're going to be interested in finding the net effect of all of that. What was the total work output? How much heat input did you need to run that cycle? Okay, so let's get to the question. I'm just going to open it up here. Okay, so state 1. We're going to use ideal gas law to get the volume, right? So volume equals mRT over P, and this is all T1, P1, M and R are constants for a given process, right? So are we given M? Yes, M is told, we're told is 0.2 kilograms. R for air, well, I don't know what that is, but I'm going to find it from the table. You should memorize it though. It's 0.287 kilojoules per kilogram. So I'm just going to, in case you didn't know, that's okay. You can still find it, is the point. So we go air, we see R is 0.287. Outstanding. Let's go back well, let's go here. So 0.2 R, we just saw 0.287, and that's in kilojoules. So whatever I get here is going to be in kilojoules. So 0.287, the temperature was 350, right? Celsius, but we don't use Celsius in the ideal gas law. So we have to add 273 to that to get Kelvin, which is 623. And the pressure in the initial state, so nothing's happened yet, is 2.5 megapascals. But because this is kilo, because this is in kilo, we have to also make sure that this is in kilopascal. So basically, this was divided by 1,000. This has to be multiplied. So we're going to do 2.5. Sorry, this was divided by 1,000. This has to be divided by 1,000 as well. So instead of times 10 to the 6, instead of expressing it as pascals, we're going to express it as kilopascals to keep it consistent. So times, that's a bit messy. 10 to the 3 is what we're looking for, though. So 2.5 times 10 to the 3. So if this were 287, which we could have done, then this would be in terms of pascals and not kilopascals. But since we left it as 0.287, the pressure has to be expressed also in terms of kilopascals. Anyways, if you calculate this, we get, let's see, 0.0143. 0.0143 cubic meters, right? That's the initial volume. Okay, now what's the second volume? Well, we're told that this is an isothermal process, right? So if we, well, let's just write out the equation here. M has not changed. R has not changed. It's an isothermal process. So T2 is T1. We can even just call it T1, even though we're really referring to state 2. The only thing that's changed, well, state has changed, but the way this change in state manifests itself in this case is going to be a change in pressure. And we're told that the pressure drops all the way to 600 kilopascals. So we're going to do exactly the same numerator. And instead of dividing by 2,500, we're going to divide by 600. And let's see what we get. 0.2 at 0.287, 623 divided by 600. And that gives 0.0596 meters cubed, of course. 0.0596 meters cubed. Okay, that's good. But now the question is, what was the work done in going from state 1 to 2? Well, we're told it's an isothermal process, right? So it's not going to be the PdV that we, well, it's not going to be the PV2 minus V1 that we did in some other questions. It's going to be what we derived for an isothermal process, which if you remember, and if you don't remember how we got there, check the other videos. But the end result is that for an isothermal process, the work is equal to P V, where P1, V1, sorry, ln of V2 over V1. Okay, this is the equation for an isothermal process, which this is. So this is what we're going to use to get the work done in this step of the process. Remember, this is a cycle, so we will have to consider the net work, which is going to be considering the work of the next step in the process. So P1 is 2,500 kilopascals. Well, actually, let's keep it in pascals. So 2.5 megapascals. So 2.5 times 10 to the 6 times V1, which is 0.0143 times the ln of V2 over V1. So V2 is 0.596 divided by 0.0143. So let's do the math there. 2.5 times 10 to the 6 times 0.0143 times ln of, I'll say 596 over 143. And I'm getting a value of 51.03-ish, 51.029. So work equals 51.029 kilojoules. Now, again, this is only the first step, so I'm going to draw sort of a dashed line here. Now, the next step is not, well, let's just reread what the question is, just to refresh our memory here, because this is a bit of a long question. The next step, if we go back, I have to find it here. So this is 4.8. We go to 600, then compress polytropically back to the initial pressure. Okay, so the initial pressure being 2,500. So now we're going to do a polytropic process going to 2,500, back to 2,500. So now, and for those who don't remember, polytropic process is basically defined by the relation PV to the N is constant. So that means that P1, or in this case, because we're going, so this is state 1 to 2. Now we're going state 2 to 3. So P1 V1 to the N, and they're telling us that N is 1.2, is P2 V2 to the N. Sorry, these should be 2s and 3s. So P2 V2, we know from the first question. So it connects back. So this is V2, and P2 is given to us as 600, right? So we know that P2, which is 600 times 10 to the 3 pascals, times V2, which is 0.0596 to the power of, in this case, N, they're telling us is 1.2, is equal to P3. Now we know P3, they said it goes back to the initial pressure. P3 is 2,500 kilopascals, or if you want 2.5 times 10 to the 6 pascals, it's 2.5 megapascals. And this is going to be multiplied by V, which we don't know, to the N, where N is, 1.2. But we can find V just algebraically, right? So if we take the left-hand side, we do 600 times 10 to the 3 times 0.0596 to the power of 1.2. And then we divide that by the 2,500 times 10 to the 3. Okay, so we're left with 8.138 times 10 to the negative 3 is equal to V to the 1.2. So if we take the left-hand side and do to the power of 1 over 1.2, that should give us V. And we're getting that V3, because now we're looking at state 3, we're looking at the end of the process that goes from 2 to 3, is 0.0181 meters cubed. Okay, that's state 3. Now, okay, we know the volumes at the beginning and at the end, right? The volume at the beginning, the volume at the end. Now we need to find the work. And the work for a polytropic process has its own sort of formulation. It all comes from the integral work equals the integral of PdV, but the way that integral gets worked out is a bit different depending on the path. Now, in the case of a polytropic process, we're going to say P3 V3, so the final state, minus the P2 V2, the initial state, over 1 minus N is the work. Now for us, we know the pressure, we know all of these parameters, we just have to substitute it in. So P3 is 2,500 times 10 to the 3, we know that. V3 we just found, that's what all this was for, 0.0181. If we minus P2 V2, now P2 we saw was 600 we started off. So 600 times 10 to the 3 pascals times V2, which we found in the first part of the cycle, 0.0596. All of that gets divided by 1 minus n, which is 1 minus 1.2. And we're getting a negative answer, okay? Negative 47.95 kilojoules. Does it make sense that it's negative? Yes, because we're told that this is a compression process. So I'm just going to box this answer, and actually I'll box this answer as well, because these are what's really important for finding the net work. But wait, there's more, because we're told in the question that we get compressed polytropically back to the initial pressure and finally compressed at constant pressure to the initial state. Why do we have more to do to get to the initial state? We're at the same pressure, but we're not at the same temperature necessarily. We're not at really the same state. And that's why this is a constant pressure process. We're happy with what the pressure is. We're going to keep the pressure the same. Now we're just going to change the other parameters to get us back to the initial state, because a cycle has to start and end at the same place. So what is the initial state? For those who don't remember, it was written in the question. It's 2,500 kilopascals, which we're at right now, which is good, and 623 Kelvin. Okay, so the initial state also for a given mass has a fixed volume, right? We know that initial volume we started with is over here. So we're basically going from V3 back to V1 isobarically, because we're told it's a constant pressure process. So I'm not even going to take a new page. I'm just going to put it in a box here. We've seen this a million times. Work equals the pressure while this is all happening, which we're told is 2.5 times 10, that looks like a 16, times 10 to the 6, times the change in volume, V2 minus V1, the final minus the initial, or in this case, V1, which is the final, minus the initial here. So 0.0143 minus 0.0181. And if we do the math here, that should give us 2.5 times 10 to the 6, 0.0143 minus 0.0181. And I made a typo. No, I didn't. We're good. So that's minus 9,500 joules. So minus 9.5 kilojoules. Again, it's obviously reducing in volume, so we expect there to be negative work done. So we're almost done. The last thing is to find the net work that was done. Now, the net work that was done is the work of all three of these together, but we have to be careful that we're using the right sign. So if we got a positive here, then we're going to do plus this minus this guy, because these are negatives, okay? We're not adding the absolute values of the work done. We want to see the net work. We want to take into account the difference between work being done to the system and work being done by the system. So we have to be respectful of the signs that we got from each step. So we'll say work net is equal to 51.029 kilojoules. And it doesn't matter the order you add them up, obviously. Minus 47.95 kilojoules, minus 9.5 kilojoules. And what we're getting is minus 6.421 kilojoules. Now this is the work, the net work over the entire cycle. And we see that it's negative, meaning we're giving to the system. We're not getting an output of the system. Okay, so you'll learn much later on, heat engines always output work. So this can't be a heat engine. This isn't a car or a plane engine. But there are systems that we give work to do something else, like refrigeration systems. But you'll see that much later.